Welcome, everybody. This is the Rotary E-Club of Silicon Valley, and every week we bring you the stories of people who are making life better for others, locally, globally, and digitally. The Rotary E-Club of Silicon Valley is part of Rotary International, over 1 million people in over 36,000 clubs all over the world working to improve their communities. In our case, our interest is doing so, especially with a focus on innovation, entrepreneurship, and education. And we are excited about seeing cool things happen that can mean all sorts of interesting things for how we protect the climate or how we help those in need. And today we have got a cool one about energy, and this one has to do with a special kind of concrete. We are going to hear from our presenter, Dr. Damian Stefaniuk, who is a research scientist at the Massachusetts Institute of Technology, the Department of Civil and Environmental Engineering, and we are very glad to have you with us. Damian, I hand the mic over to you. Thank you for joining us at the Rotary E-Club of Silicon Valley.
Thank you so much. That's my pleasure being here and having the opportunity to present our technology. So I'm really thrilled to present our groundbreaking research on concrete batteries today. I work at Civil Environmental Engineering at MIT, MIT Concrete Sustainability Hub, and EC Cube Hub. I will start with outlining two pressing challenges we are facing nowadays. Then I will show our approach, how we face these dual challenges. Then I will move to presenting our current stage of our technology, and I will end with showcasing potential applications. We've been using concrete over thousands of years, and after water, it's the most widely used material on the planet. Let me tell you that more than 1,800 cubic meters of concrete was used to build just the dome of Pantheon. We use concrete for various different structures. Mila Viaduct Bridge consists of more than 200,000 cubic meters of concrete. And another example is skyscraper Burj Khalifa in United Arab Emirates, which was built with 330,000 cubic meters of concrete. And if you think that's a lot, let me tell you that 27 million cubic meters of concrete was used to build a single structure, Three Gorges Dam in China. And so far, I've been presenting just single structures that were built with concrete. But if you take into account our whole infrastructure, our homes, built environment, concrete roads, and so on, we can end up in an estimate of 12 billion cubic meters of concrete, what we are using every single year. And the reason behind it is very simple, because no other material is as strong, durable, cheap, and available worldwide as concrete. Therefore, could we imagine a world without concrete? Personally, I could not. My first experience with concrete dates back 30 years ago, and since then I've been fascinated with concrete. Then I worked on nano and micro scales of concrete at Wrocław University of Science and Technology in Poland. Then I moved to University of Houston, where I work on sustainable corrosion resistant pre-stressed bridge structures. And finally, I joined MIT to work on multifunctional concrete. I also asked AI how it envisions a world without concrete. And this is the answer I got. However, this tremendous usage of concrete brings us to the first challenge we are facing, environmental footprint of concrete, mainly to the production of cement, the main ingredient of concrete. That huge amount of concrete we've been producing accounts for almost 10% of global CO2 emissions. And therefore, there is a huge need for finding solutions to reduce greenhouse gas emissions of cement-based material. Another key challenge we are facing nowadays is a mismatch between energy supply and demand. Whenever we want to match our demand for energy with fossil fuels, it's quite relatively easy, because whenever we need more energy, we simply burn more coal, oil, and gas. It's trickier whenever we want to use renewable energy sources. Because if we want to use solar, wind, tidal waves, and so on to get energy, we cannot control nature, and therefore we have to get the energy from nature whenever it gives us, store it first, and then use it when needed. Therefore, to fully transition from fossil fuel-based economy to renewables, huge energy storage media will be needed. To date, conventional batteries and supercapacitor technologies have been used worldwide, but they have several issues. First, minerals to build them are rare on a global scale. Second, they have CO2 environmental footprint that brings with them. And finally, they are associated with hazardous waste at the end of their life. Usually, they do not, their end of the life ends after 15 years. Therefore, our mission at MIT CE, CS Hub, and EC Cube Hub is to first reduce the environmental footprint of concrete through materials innovation. And second is the transition away from fossil fuel-based economy to renewables. And we've been doing that, and we invented at MIT electron-conducting carbon concrete called EC Cube, which we obtained by altering the original mix of concrete composed of cement, aggregate, water, and superplasticizer with an ingredient nano-carbon black. And we are using nano-carbon black due to multiple crucial reasons. First, carbon black is can be available worldwide. Second, it can be a byproduct of hydrogen production, specifically in methane pyrolysis. Third, whenever we add our carbon black product, which is hydrophobic and doesn't like water, into hydrophilic cement, it creates conductive carbon network. And what is very important about this carbon network is that it's characterized by high specific surface, which allows us to use this material to build EC Cube electrodes and then build structural supercapacitors. Supercapacitors are composed of two electrodes separated by separator and all soaked in electrolyte, for example, salt water. And for those who are not familiar with supercapacitor technology, let me give you a brief background that supercapacitors and batteries have the same purpose, to store electrical energy. But due to their different architecture, they work quite differently. Batteries work based on chemical processes, while supercapacitors work based on double layer effect, where no atomic intercalations are present. As a result, supercapacitors are usually characterized by lower energy density compared to batteries, but we can charge and discharge them faster, and then they have consistent performance over time. Last year, we were able to use our EC Cube technology and connect 3 supercapacitor cells in series and build 3-volt power supply. That power supply we charge with renewable energy source and solar panels, and that allowed us to light LED. That breakthrough pushed us to move forward with the technology and scale it up further. This year, we used Oreo-shaped design to build a column where 24 electrodes stacked in series were able to deliver us a small prototype that can power 12-volt fan, 5-volt arcade game, and can even start charging an iPhone. And let me tell you here that for this purpose, we are using 0.003 cubic meter of material, which ends up in a number of 300 watt-hour per cubic meter. And what I told you before, that every single year we are using 12 billion cubic meters of concrete, and that could result in 3.6 terawatt-hour of energy. And probably this number doesn't tell you much. So let me give you 2 examples. This amount of energy could charge every single day 50 million Tesla cars, or using this material, we could build 360 million off-grid houses, which would rely simply on renewable energy and would be autonomous. Therefore, we can see that low energy density of our material is no longer a concern, especially since it's characterized by long-term durability. Here on this graph, I'm presenting capacitance retention obtained by galvanostatic charge-discharge test, and we can see that less than 10% of capacitance loss can be seen after 100,000 of cycles, charge-discharge cycles. If we assume 2 cycles of charge-discharge per day, that would correspond to 137 years, which is much more than conventional batteries. Therefore, our technology could be potentially used to store intermittent energy from renewable sources, We could use it to build energy storing buildings shaped as desired, using, for example, 3D printing technology, or we could build self-charging concrete roads for electric vehicles. Basically, sky is the limit. To conclude, the presented technology exemplifies how innovative material science can bridge the gap between structural support and long-lasting energy storage. Second, what is extremely important, that our technology uses widely available and non-hazardous materials that can be locally sourced from virtually anywhere on the planet. And finally, this technology could provide practical solutions to pressing challenges that I described at the beginning of the presentation in development of low carbon infrastructure and energy management. I didn't share many technical details, so for more technical details, I referred you to PNA's article that we published 1 year ago, or you can read more about our technology and its potential applications, and in BBC article, Boston Globe Media, or articles published by Boston Globe Media, World Economic Forum, or MIT News. I would like to express gratitude to the whole MIT team working on this topic, and I would like to thank once again Rotary Club of Silicon Valley for giving me this opportunity to present our groundbreaking research to broader audience. Thank you so much, and I would be happy to answer any of your questions.
Wonderful, Damian. Thank you. I am excited for us to get into the questions. We'll start though by taking a look at our guests who are part of the recording tonight. I'll have you stop sharing there for a minute so I can have people wave. And so joining us from the Rotary Club of Eugene Metropolitan, Heather Edwards. Heather, always good to see you. From our own club in Houston, Texas, Roy Olson. And in Walnut Creek, California, Shag Shagrin. My name is Rushton Hurley. I am in San Jose. And Damian, I'll start the questions. So this is really intriguing stuff, right? The idea that the kinds of concrete can serve to handle the power needs of the structures that use that concrete for the building. How far are we from having buildings that are using this technology?
That's a great question. Of course, every technology brings and shows difficulties whenever we scale it up. But so far, each time we scale up technology further, with each all obstacles we've been able to tackle. Therefore, whenever we would need, let's say, small column to charge your iPhone, we can build it right away. If, of course, I talked about some applications for buildings and so on, maybe it could take a year or two, and and other applications like self-charging roads, that would take maybe even more. But we are optimistic, and year by year we try to push the technology forward and expand its practical applications and work on any limitations.
And can you tell us a little bit about how it became feasible to use carbon black for this? I think of something that is essentially widely available, and then your team essentially figured out how to make use of it in ways that hadn't before. What is it that that carbon black has confounded people with, I guess, regarding its usefulness that you guys were able to overcome?
That's actually one of the greatest questions that we've been asked, and the answer is not so simple. First, we have to keep in mind that the whole economy changes. We are converting into energy from hydrogen, and we can see that all products related to carbon products are decreasing the price in time. I remember that some time ago, carbon nanotubes, let's say, where the ton cost more than $200,000, then $100,000. Now I heard breakthroughs which dropped the price to $18,000, and that number will drop even further than next year. So all carbon products, due to that hydrogen energy production and other technologies which are simultaneously explored in the whole world, are basically giving us this opportunity to use those carbon products which are cheaper, more available, and we can control their properties much more. because we have to keep in mind that we are using carbon black, which is characterized by very high specific surface. So not all carbon black products would be feasible. And then what is also important that usually to make concrete conductive, usually fibers are used because there is a low percolation threshold, which makes it possible to make material conductive with fibers, carbon nanotubes, which are expensive, or steel fibers, and so on. With carbon particles, it's a little bit more tricky because these particles have to be hydrophobic, so they don't like water. So then during hydration of cement, they create that conductive network. And then the whole chemistry process has to be controlled in a way that we are able to achieve this highly conductive and also with high specific surface carbon network. So I would say different aspects are playing a role, and that are allowing us to soon deploy this technology worldwide.
Okay, so in pointing to the rapid reduction in costs of something like the coils, right? Is that aligned with the rapid reduction in cost related to other things that go into renewable energies? I mean, we look at the drop in solar panels costs in different parts of the world, the kind of work that they've done in China to reduce the cost of batteries. Are the same breakthroughs allowing for the kinds of reduction in cost that has enabled your team to be able to do what it's done?
We definitely can say so, because technology, for example, in building those reactors to basically tailor the properties of carbon products in methane pyrolysis, those all are basically tailored to produce massive amounts of these products and reduce their cost. At the same time, for the production of those materials, we started using renewable energy. And so basically, I would say that all pieces of the puzzle come together, and then we leverage that fact.
Well, I'm excited about that as an idea. I follow the Future Crunch, now the Fix the News World newsletter that is put out by Gus Harvey in Australia, and he focuses on these breakthroughs on a weekly basis. He spoke to our club as well. Heather has some questions. Heather, why don't you go ahead and unmute and jump in?
Thank you. What kind of resistance do you anticipate from oil companies that maybe don't want to see charged roads?
I would say that there will always be resistance to new technologies worldwide, but at the same time, we cannot. We have to work, and we have to join our forces to build greener future because of global CO2 emissions which are produced. So sooner or later, there will be no escape than use all those breakthroughs and technologies that are reducing and working on the environmental footprint. So we are optimistic. At the same time, our technology will not solve all issues, but I believe that will contribute significantly in doing so.
Thank you. If I may, another question. What do you see the market for commercial and I'm not sure if I'm going to ask this the right way, for the housing market, for commercial developers, for residential developers? Where do you see that they would be able to, I don't know where one buys concrete when they're going to make a building. So what do you see that market looking like?
I would say that based on difficulties we are aware of technological difficulties, we'll probably start with foundation because they're very well protected against environmental impact. And then we'll move to columns and other structural components. We can, for example, use, now the estimate shows that 33 meter cubes of concrete will stand enough for a residential house, which is basically a foundation of a house. But that technology can be expanded further. I think it can find amazing potential in building data centers, where not only energy storage, but also energy stabilization is needed. Basically, the main function and the primary function of supercapacitors, where we can do both. So I would say, but we are trying to explore other opportunities as well, and step by step see where we can fit with our technology.
Very cool. So if it's in the foundation of a home, would it functionally be the same as solar panels, that it's hooked up to the electrical grid of the home, so that's how you're going to charge your washer and dryer and your electricity and your TV, that it would be integrated into that system?
Yes, the main function would be that our multifunctional material will serve two primary functions. First, structural support as regular foundation, plus at the same time, energy storage. So if we imagine off-grid house, which has solar panels on the roof, and then it's not connected to the grid, then whenever during the day there is sun, we can get the energy from nature, store it during the day, partially use it, partially store it, and then during the night use that energy storage. So that would be essentially function. And currently we are using regular batteries for that purpose, but we want to avoid them because every 15 years we have to replace them. So for us, if we build a house which can last 50 or 100 years and can have that function of supercapacitor there, and we can get rid of those batteries, replace every 15 years, for the environment, it's great. Especially that at the end of the life of the structure, we do not have to dispose of this material because it will still be there as foundation, serving as structural support, even if it loses that energy storage function.
Amazing. Thank you.
Thank you.
So, Damian, one of the things that we regularly focus on in discussions with our speakers is how partnerships work in allowing for innovation and sustainability. We've had wonderful speakers talking to us about everything from dark skies initiatives to using idle oil wells for the ability to just make things better in the community. When you think about the partnerships that your team at MIT has engaged in order to move on the research that you've done, are there partnerships that were especially important for developing the breakthroughs that you did?
I would say that it's always a combined effort. The technology developed at MIT, we are sponsored by whole MIT CS Hub, CE, and now EC Cube Hub. So I would say that equally every entity is a part and it's important to us. So I couldn't just point out one of them.
Fair enough. It's certainly our hope that you will have the opportunity to use your technologies with organizations that are doing housing programs. We had a group speak to us a while back on 3D printed homes happening in different parts of the United States and around the world, and it seems like an exciting space for possible partnerships as well. In talking about breakthroughs, we always I think need to talk about the people who help make the breakthroughs happen. As an educator, I'm especially interested in what may have inspired you along the way to get involved in the research that you do. I know that you're a civil engineer, that you've been involved in designing bridges, different things. But was there a point along the way at which you got excited about the potential for this line of work?
I've been working with concrete for decades, and I had different projects. But when I was at the University of Houston and I heard about this particular project, it inspired me, and I really wanted to get on board. So thanks to my PIs, Professor Franz Ulm and Professor Admin Mesic, they accepted me on the team, and since then I tried to do my best to push this technology forward, especially that the environmental footprint, and there is a mission behind it. It's not just regular science. It's something that can help people out there. I could not imagine a more exciting project and more impactful project.
I love that there's a focus for you, and probably a good place for us to wind down the recording. I'll finish some things off and then hand it back to you for the final word. But for all of you who have been watching this, thank you as always for taking your time to watch our videos on YouTube or on our SiliconValleyRotary.com page, or listening to our podcasts, whether it's the development success stories or the Inspiring Solutions for a Better World podcast, or the Digital Rotarian as well. We love that we are able to get so many different ways of thinking about new possibilities for communities in front of you. And we ask that you take an interest in the kinds of things we do. You can find us at rotary.cool, which is a shortcut that will get you to our main page. If you are on our Rotary page, we hope that you'll leave a comment in the section at the bottom. This is one of the ways in an online and asynchronous, geographically distributed club that we get a chance to share ideas, and that you will share your ideas on this program or any other element of the meeting in that space. Damian, we always hand it back to our speaker for the final word. What would you like people to have in mind as they finished watching or listening to this recording?
So if I can share screen one more time, I would like to end up with a short message that I would like you all to take home, because I would like to all of us to unite, join our forces, and build a greener future with cutting-edge solutions such like EC-Cube technology, concrete battery. The technology will poised to revolutionize energy storage. Thank you so much once again for this opportunity.
A wonderful finish, and everyone, we will see you next week.